Hello and very good evening. Good afternoon and good evening to Richard Noling. I think you are watching this live show and I have just received your message. Hello, sir. I managed to get a nap this afternoon and evening, so could be awake in time. Thank you for streaming. Almost 12:15 a.m. Okay, that must be late night. So I mean to say you can watch this live streaming, but you really do not, expect you to be wake till late night because you can watch it later also. So thank you for being here. Okay, so the agenda of today was to carry on with the things that we are actually dealing in terms of classical physics. Oh, I received a WhatsApp message. I don't know, somebody sent me a message that what are you going to cover in this lecture? Okay, so what I will do tomorrow or maybe day after tomorrow, once I come online, I will like to show you the entire agenda. What are the things that I'm covering in this lecture series? So somebody asked whether it is class 11, 12. Yes, it is. If you talk of the standard, I like to awake at this time anyway. It is nice and quiet. Okay, great. So it is good that I will be covering the 11th and 12th standard apart also, and a lot of physics in the coming part. So yes, there will be a lot of things which will be covered. I will share. I understand that people are a little bit apprehensive because they really don't know that what is going to be shared, what are the things that I'm going to teach. A complete kind of a lesson plan. I think that is what they are looking for. Okay. So today, what I would do is that I would start with this part, which was earlier we started with the system which has got heads and tails. So, and we started that if it got a head and then it moves to tail, HT, and if it start with tail, it moves to TH and TH. Now, what I'm going to do today is that I am going to share a little bit complicated, I won't say complicated, a kind of a complex system. And in order to generalize the system, I would increase it and make it a kind of a dice. Right? Okay. So even before making it a kind of a dice, what I would like to tell is that these dynamical laws, I mean to say, for example, okay, let me show you the Jamboard, then it will become clear. So this dynamical law, then this dynamical law, then this dynamical law, and this dynamical law, all those dynamical laws can be actually written in what is called a degrees of freedom. And what is that degree of freedom? This is what I'm going to talk over today. So if, for example, if we consider a specific coin, say, for example, I consider this kind of a coin, okay, and I would denote this coin with a degree of freedom, and I would use this symbol as sigma. Okay, so the point is that our coin has one degree of freedom, which we can denote by the Greek letter sigma. Sigma has only two possible values, that is, sigma equals to 1 and sigma would be equals to -1. So we have got a coin and we have got a degree of freedom, which I'm trying to tell, and it has got a sigma equals to 1 and it has got a sigma equals to -1. So this sigma equals to 1 will denote what is called a head, and this sigma equals to -1 will have something which is called a tail. Right. And also we will use a symbol to keep the track of time. So for time we will conventionally use what is called t, right? Okay, so we use this symbol t in order to denote the time, that means evolution of time. And here we have a discrete evolution. For that, for this discrete evolution, we will use something which is called n. So this would be the time part, t, which will be equal to time, and this would be the discrete value, which will be n. Well, let me see if I can put myself a little bit lower. I don't know how to do that so that things become, just a second. No, not this one, this one. I don't know how I did it. Actually, my position was reduced to below. How to do that so that this part becomes much more visible. Just hold on, I'm trying to do. No, no, not this one. Either this one, not this one. Anyway, okay, so it evolves with time, which is t, and it has got a discrete value which is denoted by n. So the state of time t is I mean to say the time state at time n, that means this value is being actually shown by this figure sigma n. Okay, so sigma n, I mean to say what it actually tells. We have a discrete evolution which is n, we have a time which is t, and the state of time n is described by the symbol sigma n, so which stands for sigma at n. So I can tell this one to write it in very simple language, sigma or at n. Okay, this is what it tells. So the value of sigma at n, and n denotes the discrete position. Okay, so if we would write this evolution of two laws, the first law says that no change takes place. So if there is no change taking place, then the pattern would be this one. Sigma n plus 1 will be sigma n, obviously, because here nothing is changing at all. So this symbol equation means what? It means that the value of sigma at the nth step, it will have the same value at the next step. So the value of sigma, this value of sigma at the nth step will have the same value, of the next step. So that is what this equation all means. Now the second equation of evolution obviously has the form of this. It will have a form of this. Let me move this with the eraser so that this becomes much more clear. So it will have a value of this one. Okay. So, and in this way we can add further and further and further in order to go that. So, but in, I mean to say, in case of the future behavior is completely determined by the initial state, and that is why we call these laws are deterministic. Now, in order to make things more interesting, now this is basically one evolution time and one part of the coin which has sigma at n, and this is no change, and it further goes for a change. That means there is a minus sign, that means it comes for a t and then for a head. But what about a typical kind of a thing where we add certain more complexities? That means what I'm trying to tell is that to generalize the system by increasing the number of states, instead of a coin, I am going to use what is called a dice. Okay, and this dice, I'm so sorry, this dice will have a lot of implications, and this will actually tell us the evolution of systems. So first of all, I would like to tell that there will be great many possible ways in which this dice will evolve. So right now I am actually going to show you the system in which this dice is going to take forward. So first, let me show you. This is actually the dice which I have taken. I'm not making this big, otherwise things will be a little bit bigger. Now, what I'm trying to show you is this kind of a figure. Okay, I will move this one later. Okay, this is, I hope this is visible to all of you, right? So this kind of a figure. So if we start now in this kind of a figure, if you see that it has got an endless cycle. This one, 1 2 3 4 5 6. Okay, so the simplest way is basically to have this kind of a figure, 1 2 3 4 5 6. And what happens over here is that in this figure, you see that it goes from 1, then it goes to 2 3 4 and 5 and 6. Now if I take this part, okay, I just made it a little bit bigger for you. Okay, let me make a little bit bigger. Yeah. So here you see what happens in this 1 2 3 4 5 6. So this is actually has got an endless cycle because it keeps on going and going and going. Now, for example, I will take my brush and I will start at point 3. Now, if I am starting at point 3, sir, for example, what would be the system? It will go from 3 to 4, then from 4 to 5, and then from 5 to 6, and from 6 to 1, and again from 1 to 2, and then from 2, and so on, right? 3 4 5 6 1 2 3 4 5 6 1 2, and it goes on and on. So it is a kind of a constant repetition things which you're moving. So we may call this as first dynamical law. Okay, now in order to show another dynamical law, this is one law which has got, so I have taken this part of the cube and I've plotted in here. So whatever it goes in a kind of a cycle. This is one. Now let me take this kind of a figure. Okay, I will just remove this and I will try to make this one a little bit bigger. I hope this part is visible. Okay. Okay, I will move these also a little bit far apart because this is not required right now. I will focus on this. Okay. So what this figure actually tells, this figure is actually telling that if I go for the second part of the law, so if you start with one of them, you go to the another, right? So nevertheless, this law. So now if I start, for example, at point 2, now I will take a different color because it's already red. So if I try to take at point 2, okay, I'm sorry. I think this is 2 to 1. No, 1 to 6, 1 to 6. Yes. So if I start at 2, for example, from here, so I have one chance of going from here to here, and then I have a chance of going from here to here, that is second. Then I move from here to here, third, and from here I have a chance of moving here to here, 4, and then I have a chance of moving here, and then I have a chance of moving from here to here. That means I have already got what are called 6 possibilities. These are basically 6 possibilities we have got, and the cycle, I would say, will be endless because it continues and continues and continues and continues. So this is what is another kind of a dynamical law. So if I start at 2, then 6 and 1 and 2, so it actually keeps on going and going and going and going. Now, if I take another dynamical law, for example, let me show you this one. I will remove this one and this one. Now, this is something different. So here you see, if I start at 2, okay, I go to 6 and I go to 1 and again I come back to 2. That means I won't be ever able to reach point number 5. Again, if I start at 3, I go to 5, I go to 4, and again I go back to 3. I won't be able to achieve either 6 or 1 or 2. That means that if I start from any part, say for example, even if I start at 5, say for example, the history, if I start at 5, the history would be 5 to 3, 3 to 4, 4 to 5. That means I am never going to get at this point, that is point number 6. What I'm trying to show you is that this is the way in which the dynamical laws are actually laid out. In case if I start at 4, then I go from 4 to 5, 5 to 3, and again back to 4, and I won't be ever able to go anywhere else. Similarly, so that means what? This has got actually 3 possibilities. Let me put it a little bit bigger. 3 possibilities mean the sense that if I erase those things, you see what are the 3 possibilities. You can put it over here. One possibility is basically this one, this one possibility. The second is this, and the third is this. So 1, 2, 3. These are only 3 possibilities. Okay. And this one actually shows how many cycles are there. That we need to find out. So how many cycles are there over here? There are only 2 cycles. One is this and one. Now this is very important for our understanding, because once we move from here to quantum states, etc., these things will be very important. Now, if I take this kind of another dynamical law, say for example, if I take this one, let me make it a little bit bigger. So here again, you see it is coming from 6 to 5 and going from 5 to 6. It is going from, again, this from here to here, here to here, here to here, and this is just going back to here. Right. So in this way, I mean to say, we can lay out different types of dynamical laws, but it is extremely difficult that where will we go and where will we land. So I just try to show you 3, I mean to say, dynamical figures. So the first dynamical figure, which is this one, shows 6 possibilities. Second one is 3 possibilities, 1, 2, 3, and the cycles goes on, and that is how the other other cycle also tells. So the first one, it has got an endless cycle. So if you start with 3, 4, 5, 6, 1, 2, we can go on. Then this figure actually shows that the dynamical it looks a little bit messier, but I think that is quite good enough. And then, if I go to this kind of a figure, this figure, which is this one, this particular figure, that is here you will see that dynamical, this has got 3 cycles, as I told you. I mean to say, sorry, it would be 2 cycles, because this is 1 cycle and this is 1 cycle. This part, this is 1 cycle complete, and this is 1 cycle complete. Cycle means if you are coming back, this has got endless cycles, but it has got only 2 cycles. And then I showed you this part. This is also a different kind of a figure. Okay, so now what we do is that we will try to see into something which is called the rules that are not allowed. Rules that are not allowed are what? That means that we should remember that it is enough for a dynamical law to be deterministic, it must also be reversible. That means what I'm trying to tell is that according to the rules of classical physics, not all the laws are very legal. That means it is not enough for a dynamical law to be deterministic, but it also has to be reversible. And by the law reversible, I'm trying to mean is this: if you reverse all the arrows, the resulting law is still deterministic. Another way to say is the laws are deterministic into the past as well as the future. Because let us remember what Laplace demon actually told, that for such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Now, the question is that can one conceive laws that are deterministic into the future but not into the past? Can we formulate these type of irreversible laws? Definitely we can, and for that I would like to show you this kind of a system. And allow me just for some time to explain this system so that it is possible. Now in here you see this figure actually does tell you wherever you are and what to go. Now say for example, let me make this one a little bit bigger. Yeah. So here what happens is that, for example, let us say if you are at 1, you go to 2, and from 2 you go to 3, and from 3 you come back to 2. This is quite okay. There is no problem. So 1 to 2, 2 to 3, and from 3 you go to 2. There is no ambiguity in the feature, but the past is different, is a different matter. I mean to say, what if I am standing, okay, let me remove those lines so that it becomes a little bit clearer to you, because I have to draw some lines. 1 to 2, 2 to 3, and 3 to 2, we are going back, etc. Okay, now say for example, if I am standing over here, I will use this pen. Say for example, this is a human figure. Sorry for my, yeah. So suppose you are at point number 2. Now, can I tell that where I was before that? Can I tell that where I was before that? You could have come from 3 or from 1. But the thing is that you see this arrow only shows in this direction. So suddenly, if I am at 3, the diagram does not tell about my past. I mean to say, even if in terms of reversibility, there is no way in which I can go back to 1. I cannot go back to 1. This is not, because the arrow is only showing this. But the thing is that if I am at 2, for example, if I'm standing at point number 3, right here, then I can say that my past was 2. That I came back because there is an arrow which is going back to point number 2. But at point number 2, when I am standing, there is no way in which I can know where I am coming from. But I can tell that where I am going, that is, I am point number 3. Now, this type of a figure, or I would say this type of a dynamical system which we are talking about, is something which is called irreversible. Okay, this is irreversible. That means I cannot reverse it back. And this kind of a situation, I would say, is prohibited by the laws of classical physics. Let me put it over here. Is prohibited by the laws of classical physics. We cannot do that because, as I told you just quite a few seconds back, that it tells that there should be a thing, the Laplace demon tells that I have to, and there should be a way in which I can get the details. Do we have any information about the state transition rates? Or probabilities. No, Richard, we are not talking of the rates or probabilities here. We are not at all talking anything about probability. This is absolutely a deterministic system. So we are talking only about the right determinism, whether there is something which we have got a past or got a future. Right, I hope I can make yourself understand. So this is one which is prohibited by classical physics. This is something which is irreversible. Okay, now I would like to go back to this kind of a figure. Okay, I will make a little bit bigger. Okay, now you see that this is a very simple way that it tells that from, if I am coming from point number, standing at point number 2, say for example, they have got a past because I have already got a arrow which is moving towards 1. I have got a arrow which is coming from 3, and I have got an arrow which is going towards 3. So here is basically what I'm so sorry, which I'm trying to tell. I hope this is visible to all of you. If every state has a single unique arrow leading into it, so remember this is one state, okay, there should have a single unique arrow leading into it. That means, is there an arrow leading into it? Yes, there is an arrow into it. Is this point number 3 has an arrow into it? Yes, it has got an arrow into it. Then it is a legal deterministic reversible law. Also, there must be one arrow to tell where you are going to and one arrow to tell where you came from. This is something which is very important. So now you see that in order to define what is called a reversible system, the first thing that in this figure is that, now here again, the important thing that you see is that if this arrow, instead of coming here, if I reverse it and make this arrow, then we get this kind of a figure, because you see here is one arrow. Now again, if I reverse this arrow which is going to from 3 to 2, if I make it from 2 to 3, again you go back, you see we have got this figure 2 to 3. Isn't it amazing? Again, instead of this arrow moving from 2 to 3, if I make an arrow moving from 3 to 2, again we go back to this one, because this has got a 3 to 2. Okay, yeah, when you saw the dice, you got confused. Okay, so what I'm trying to tell over here is that, okay, I will just move away myself from the screen. My audio won't be visible. Take a look of this. I hope this is clear now. So this is something, this part, if I, that means this is actually a deterministic reversible system. And if I reverse those arrows of the deterministic reversible system, this becomes again a irreversible system. I will just put it on a fresh one, and I will again try to show you by making those things a little bit smaller, because it is better that you see both of those things together. Okay, now you see the difference. Now you see the difference. So what happens in the first one? What happens in the first one? This is, I mean to say, most of the classes, they miss on this thing, what is reversible and irreversible, but this should be the first thing which should be taught in a classical physics class before going into calculus and everything. So this first figure does tell you wherever you are, where to go. It tells that you can move from 1 to 2, and you can move from 2 to 3, and if you're standing at 3, you can move back to 2. But the question is that if you are at 1, you go to 2, from 2 you go to 3, and if at 3 you go to back to 2. There is no problem with the future, but the past is different. Suppose I assume that you are at point number 2. Then the question is that where I was before that. That means this can be called as a irreversible system. This is what is prohibited in the laws of classical physics, that this is an irreversible system. Whereas I copy and paste it, this would be called a reversible system. And the basic feature of the second figure is that if I stand at point number 2 over here, I know where I came from and I know where it goes to. If I stand at point number 3, I know where I came from, but because there is no arrow, I don't know where to go. But still, I know the past, which was not clear over here. So the most important thing also is that these arrows, so what I told you, this is also important. Let me copy this part. In order to make a system which is reversible, if I get something like this, if every, okay, I will just make this one little bit go lower. So, and this one, so if every arrow, every state, this is a state, and remember this type of state we will also deal with quantum mechanics. So if this is point number 2, every state has a single unique arrow leading into it. That means there should be an arrow which will be coming towards it. This is one, and also 3 has an arrow coming towards it, and a single arrow leading out. There is an arrow which is leading out. This one, this is leading into it, and this is leading out. Then it is a legal deterministic reversible law. There must be one arrow that tells you where you are going, and there must be one arrow which will tell you where you come from. I'm so sorry, this is too big, so it won't fit over here. So here it is. If I delete and make it move over here, this would be fairly visible. There must be one arrow to tell where you are going and one arrow to tell where you are coming from. So the fact is that the rule that dynamical laws must be deterministic and irreversible is something very central to classical physics. I'm sorry to use this word, but we forget to mention when we are teaching classical physics. Now, question is that what would we call? Shall we call it as the first law? Shall we call it the second law? We already have Newton's first law. We have a zeroth law in thermodynamics. In the second figure, why there is no arrow leading to it? Okay, in the second figure, that's a good question. There is no arrow going out. I mean to say, 3 has got the arrow, but 2 hasn't got. 2 hasn't got because at point number 2, I know the past which is coming. That means I came from here. But here you see the arrow which is going out over here also. But this one has got no arrow. That is why I've got no past. That means this particular figure, this 2, 1, 2, this has got no past because it only shows something which is coming from, but this one shows something which is going, right? So this has got towards this has got opposite to this has got towards this has got opposite to it. Are you getting my point, Richard? So this arrow which is going from 3 to 2, this one going from 3 to 2, and this has also got something which is coming from 2 to 3. This would be the reversible system because I can reverse back. As you can do, 2 is also going, I know the past. Reversible means what? That I have to trace back somewhere, but here I am unable to trace back anything because only I can trace back to here. Now if you're asking that why this has not got another arrow, this is because I have made it small. Otherwise I have again have to include a system like maybe 0, and so I just tried to make it a little bit shorter with 3 systems. Okay. Yes, 1 goes to 2 and also comes from 2. Yeah, absolutely, Richard. I'm great, happy that, I just wanted to share one thing very personal with you. I hope you won't mind. You are all like my children. I got a realization, is something not very much which is related to physics. Okay, anyway, let me go back. I will share with later. So that is what this is an reversible system, and this is a irreversible system because from point number 2 I have got no past, but on point number 3 I've got a past which is coming. So remember this thing, there must be one arrow to tell you where you come, and if every state has a single arrow leading towards it. But unfortunately this is not being taught. So this is something which is really been missing in the standard classical physics classes. So I would take a pause for today, and what I would like to talk next, maybe tomorrow, I'm not very sure, maybe day after tomorrow for sure, is something which is called in dynamical system with an infinite number of states. Okay, so we talked about a finite number of states, this one. Okay, this is something which you have got. Then we talked about this one. So these are all either 1, 2, 3, 4, 5, 6 possibilities, or 6-sided die, or something which has got a head or a tail or something. But what if that we got a huge number of, yeah, thank you for streaming today. You will get the update, Richard, in my community tab where I keep on posting about when I am coming, etc. So what I was telling, a little bit personal, apart from this physics, etc., is that one thing I have found it personally is that medicine actually cannot cure you from all kinds of disease. I mean to say, I don't want to tell, but in the recent past, from December, I was not feeling well, etc. There were a lot of weight which have got increased, so there was a little bit of blood pressure which also came in from my side. But what I found, it is little bit tough, and which is eventually also going for about 2 months or so. That if you really do a lot of physical exercise, I mean, there's a certain cases you really can overcome all the health issues, to be very honest with you. And I have done that, and I have been really blessed because my wife cooperated in terms of food restriction, and I did a lot of jogging and still doing, I don't know. So it actually helped me a lot. I mean to say, if you're really suffering from anything like obesity or high cholesterol, etc., although this is nothing related to physics or mathematics, I think doing a lot of food restriction and doing a lot of physical exercises actually brings down a lot of things, and you get a very good health. At least till now, by God's grace, I have been benefited. So anyway, thank you. I know there were very less numbers of viewers who are present today, but not an issue. Richard, you are there, so slowly it would increase. So next time we are going to deal about what is called if we have got a state which has got infinite number of states. Once this is done, then we are going to deal with the coordinate geometry, which will start with the vectors, a little bit of trigonometry, and so on. I firmly agree medication helped me, or maybe 20-30%. Yes, and I can tell you, Richard, my doctor gave me a lot of medicine for my blood pressure and cholesterol. He started that immediately you have it. Me and my wife, we all disagreed to him. And believe me, it is tough because I am actually not a born vegetarian, but I gave up all the non-veg food, and it helped me a lot. And morning exercise, running, a little bit of jogging and walking around, it has reduced everything. I mean to say, I feel much better. If you see my earlier photographs when I am live streaming, you will see a significant change in my physical terms because I'm slowly going to have much more thin. Yeah, I look towards this. I have not done any quantum mechanics in reaction network trap. Yeah, so quantum mechanics and everything I will do slowly. Only thing is that you have to follow this slowly, one by one, step by step. Because Richard, you will see I mean to say, state of a system, reversible, irreversible. These things you will see most of the books they miss. Pick up any book on classical physics that will start with Newton's laws of motion, second law, third law, derivative, vectors, all those things. But this is the foundation. Until you know what is a system, what is not a system, reversible, irreversible, all those things, I think it becomes very superficial to learn all those without having a reason. Anyway, because it is a live streaming, I think it will make into a good video also. Yeah, one brick at a time. I tell my students, okay, so what do you teach, Richard? I mean to say, when you're talking to your students, what actually do you teach? Do you also teach physics and mathematics? I think you're also from Ireland. You told that day that you're from Ireland. So anyway, so I would like to know that what do you teach, because it is good to meet a teacher also. Okay, so thank you very much, and goodbye, good night, and wish you all the best in terms of your health and everything. And I help undergraduates in our university maths drop in Central Australia. Okay, great. That's wonderful. That's wonderful. So you're doing a great job. Thank you. Thank you for logging in, and do stay tuned. Also, I would like to give you lot of first and second year maths engineering. Okay, so also what I would like to tell you, Richard, is that you can also look into this channel where I do a lot of streaming also. And here I am also taking a step by step towards making you understand about general relativity, where I have just started with spherical and polar coordinates. So I will be doing a lot of mathematics, basic level mathematics from there. And then I will go into Einstein general relativity. Although you can watch the previous streamings of mine, which is more on the mathematical part, something general relativity. But I got frustrated. I thought that I should take a one by one step forward towards learning. So this channel I am on at around 8:15 p.m. Indian Standard Time, 8:15 p.m. So you can check out with Australian time. So that is also there. I'm coming and teaching all those things. I know that I'm not doing a lot of videos, my views, etc. All those things are going down. But making up good tutorials in classes are also very good, because that is the way I really plan up. So to next class, I will do all the infinite sum of states and then add up all those things. And next to next class, I will sum up everything, all those things in one simple class. And then I will go to the coordinate geometry, vector spaces, trigonometry, linear algebra, and so on. So thank you for watching, and we wish you all the best. Thank you very much.